So let me first take the what you call example. Okay, suppose if you have a radioactive decay problem. Okay, in that case, so in case of a what you call radioactive decay problem, suppose you have suppose there is one radioactive substance. Suppose I have one question. What is the probability? What is the probability of getting 50 counts? Okay, 50 counts in 2-second interval. Is that okay? You have some radioactive substance. Okay, so again you are observing that one for 1 hour. Okay, so just divide that 1 hour into 2-2-second interval. Okay, 1 full hour, divide that one into 2 seconds plus 2 seconds and so on, up to 1 hour. Okay, so now in again, suppose you are observing that counts. Okay, in 1 2-second interval you may get 50. In 1 2-second interval you may get 100. In other 2-second interval you may get 20, like that, isn't it? You can get anything. Are you getting my point? So again, there we are asking the question that what is the probability of getting some particular number of count in one time interval? That probability will be very small actually. Are you getting my point? And that probability will be constant also actually. Is that okay? So the question is, you have a radioactive substance. I suppose you have some scintillation counter or something. You are observing the counts. Okay. What is the probability of getting 50 counts in 2-second interval? Okay. Suppose let me take one practical observation. Practical observation is I have 1 hour here. Okay. 1 hour here. I'm going to divide that one into 2-second interval. Okay. And I'm going to observe. So in one 2-second interval you may get 10 count. In other 2-second interval you may get 22 count. In other 2-second interval you may get 1 or 2 count. It's all random here. Is that okay? We are going to apply this distribution in case of whenever there is a randomness actually. It's all random, am I right? So when this happens and when this kind of situation exists, okay? So the question is, what is the probability of getting 50 count in 2-second interval? Or simply, what is the probability of getting 50 count in 2 seconds? Or in any one particular 2-second interval. Time interval, I'm talking about time interval. And that probability will be very, very small actually. Probability of getting some particular count in one time interval. So to observe that one, I think you may need to observe for a very long time, isn't it? Speak out. So that's why, look at here. So we apply this whole idea of Poisson distribution when probability is small and constant. When probability is small and constant. Yeah, speak out. So you have one radioactive substance, okay? And you are observing using what you call counter, okay? Some either Geiger counter or whatever, okay? Scintillation counter will give count, isn't it? I think, yeah, whatever. So it all depends on the what is the sample you have, okay? Now what I'm saying is you are observing that one for 1 hour, okay? In 1 hour it might have given millions of count. In first 2 seconds it might have given 10 count. In second 2 seconds it might have given 100 count. Next 2 seconds, next 2. It's all random, am I right? How many counts that it gives in some particular time interval. In that kind of situation, okay, we can talk about probability of some n counts, okay, in some 2-second interval. Probability of getting some particular value of count in some time interval. Then we go for that one, and that will be very small. That probability will be very small actually. Is that okay? Wait a second, we shall apply that one, okay? Once we apply, you will understand this one. So try to read out some book or something about this one, okay? When probability is small and constant, we are going to apply this one. Is that okay? Wait a second, I'll tell you in what approximation to binomial expansion you will get into this one later, okay? First we shall work out this one, okay? So now look at here, let me define this one. An event can occur, an event can occur, so 0, 1, 2 and so on times, either 0 or 1 or 2 times in an interval. In an interval. Okay, so interval means time interval. Okay, in a time interval. Is that okay? Just like you can get 1 count, 2 count, or 3 count in 2-second interval. Am I right? Very random. Is that okay? An event can occur 0, 1, 2, and so on. Okay, n times. Let me write n here. N times in a time interval. Okay, it can occur. Possibility. Okay, event can occur. So in a time interval, let me call the time interval as tau. Okay, let me call the time interval as tau. Is that okay? So now look at here. This is the situation. Okay. Now again we define the average number of events. Look at here. Let me write in different. So we define lambda. Okay, lambda is average number of events per time interval tau. Average number of event per time interval. We call it as event rate. Look at here, that is named as event rate. So let me write per time interval. Okay, or average number of event per time. Let me write like this. Okay, average number of event per time. Simply. So just strike out other part if you have written. Okay, we call this one as event rate, or I think rate parameter. Okay, event rate or rate parameter. Okay, 1 time or 2 time or n times in a particular time interval tau. Okay, and for that whole what you call process, you define the average number of event per time. Okay, this is required. Now look at here, probability of observing n events. Okay, n events in time interval tau. Is that okay? In time interval tau, we are going to write it like this. Okay, P of n events in time interval tau, that's equal to lambda into tau whole power n e power minus lambda into tau divided by n factorial. We can derive that out, or we can start with binomial distribution. We can end up with this one actually. Is that okay? Speak out. Probability of observing n events in the time interval tau. Now look at here. Once you write this probability distribution, okay, observe this one. This lambda into tau. Am I right? Look at here. Yeah. Wait one second. Lambda into tau. This should be dimensionless. Am I right? If you write any exponential of something, isn't it? This should be dimensionless, isn't it? So that's why if tau is in second, okay, if your time interval is in second, you should find lambda per second. Average number of event per second. You should have found like that. Okay. If tau is in hour, you should find lambda per hour. Is that okay? So because look at here, it is e power minus lambda into tau. This should be dimensionless. Is that okay? Or this lambda into tau that came here. This is the probability. This should be dimensionless. Am I right? To have dimensionless, this lambda and tau together, again, if tau is in second, okay, lambda should be per second. If tau is hour, lambda should be per hour. If tau is day, 1 day or something, 1 day, 2 day, it should be per day. Lambda should be per day. That you need to take care. Is that okay? We define it like this, but in the definition, you need to remember one point, that if this is second, this is hour, then it will not work. Is that okay? Speak out. Yeah, look at here. An event can occur 0 time, 1 time, or 2 time in some time interval t. Okay, just like you take radioactivity. Okay, count again. So in some 2-second interval or in some 5-second interval, you can get 1 count, 2 count, n count. Am I right? Anything can happen there. An event can occur 0 time, 1 time, or 2 time, or n times in a time interval tau. Okay. So lambda again. So for this whole what you call process, okay, I am going to define average number of event per time, lambda. We call that as average number of event per time, or event rate. We call it as event rate. Rate, I hope you know, per time, isn't it? Or we call it as a rate parameter also. Is it okay? Rate parameter. Now look at here. So in such case, probability of observing n event, n can be 0, 1, 2 like that, okay? Probability of observing n event in the time interval tau. So that can be written as lambda into tau whole power n e power minus lambda into tau n factorial divided by n factorial. But care should be taken while finding this lambda. If tau is in second, lambda should be per second. If tau is in hour, lambda should be per hour. If tau is in day, lambda should be per day, because this should be dimensionless, isn't it? This is a probability. Exponential of anything that should be dimensionless, isn't it? That care that you need to take while applying this one. Is that okay? The problem is we are not deriving this one. That's the problem actually. Is that okay? Just try to remember the definition, try to apply that one, okay? Now let me take one example.
How this includes the probability is small?
No, we can apply this one to the situation when probability is small. If probability is large, this will give error actually. Is that okay? Again, we shall see that one. I'll give you some more reference, okay? This can be applied in, again, because while deriving we do many approximation, okay? That is this approximation. Are you getting my point? While deriving this expression, we do many approximation. It's not direct one, okay? So there we have to take probability small and constant actually. Wait. Here, while applying this one, we will not talk about number of trial, okay? While applying this one, we just talk about probability of getting n event into, okay? If you start with binomial distribution, if you go for this one, then you talk about number of trial. Okay, let me talk about that one. Here we don't talk about trial. Are you getting my point? To experience this one, you have to go for number of trial. How many trial you need to do? If probability is too small, obviously you need to go for very high number of trial to show that one, isn't it? It's a very obvious fact, isn't it? So that's why that's a different story. From binomial distribution, approach is different. So this is the basic definition of Poisson distribution. Is that okay? Yeah. So we apply this one whenever the probability, whatever we are talking about, is small and constant. Okay. Yeah. Now we shall apply this one for some particular situation. There are on average 20 buses per hour. Okay. I think some just question. There are on average 20 buses per hour at a point. Okay. An average 20 buses per hour at a point. Okay, at a point. But at random time. But very randomly. Okay, 20 buses per hour at a point. Okay, but very randomly. Okay, sometimes all 20 buses may come in the first 5 minutes. Or sometimes all 10 buses come in the last half an hour per hour. Am I right? In 1 hour, 20 buses will come very randomly. Is that okay? Yeah. So like that here KSRTC does that one actually. They this Ramnagar bus, okay, 3 buses will come together and they go together. Next 1 hour, no bus. But they follow some consistency, but this is random, okay? Yeah. Yes, now look at here. The question is the probability that there are no bus in 5 minutes. The probability that there are no bus in 5 minutes. Or you can talk about probability there are 1 bus in 5 minutes. Probability there are 2 bus in 5 minutes. Again, this is the question that they asked in that particular question. Okay, you can just generate other question. Is that okay? Probability there are no bus in 5 minute interval. Is that okay? So what is that one? Now look at here. So there are average 20 buses per hour. Am I right? 20 buses per hour. Lambda is equal to 20 bus per hour. But probability is asked for this time interval. Am I right? Per minute. You have to convert this one into per minute. Okay. So 20 bus per hour. Am I right? 1 hour. 20 bus. Speak out. 1 hour can be written as 60 minutes. 1 by 3. Speak out. 1 by 3 per minute. Is that okay? 1 by 3 bus per minute. Can I say like this? So that after 60 minutes, 320. Yeah, 20 buses, isn't it? This we call this as a rate parameter. Okay. Why I'm converting per minute? Because he asked 5 minute. Again, he asked time interval in terms of minute actually. Is that okay? That's why I have to do that. Now the next question is, what is the probability of getting 0 bus in 5 minutes? Am I right? That's equal to, speak out, lambda tau whole power n e power minus lambda tau n factorial, n equal to 0 here. This equal to lambda is 1 by 3, tau is 5 minutes, per minute into minute. Okay, raised to 0 e power minus 1 by 3 into 5. Check this out. Whole divided by 0 factorial. What is this one? 1 by e power 5 by 3. Calculate this one quickly. Someone. Your calculator. 0.18. 0.18. Okay, nearly equal to 0.18. That okay? So now similarly you can find probability of one bus, probability of getting one bus in 5 minute interval, in tau equal to 5 minutes. Okay, so now that's equal to, look at here, lambda tau 1 by 3 into 5 raised to 1. Am I right? So e power minus 5 by 3 divided by 1 factorial, isn't it? You can do this. Like that you can proceed. So whenever there is a randomness, we deal with this one actually. Okay, yeah, speak out. Now look at here, to verify this one, okay, you need to go for very large number of trials. That's what he was trying to say, when number of trial is large. Okay, if you want to verify that there are 0 buses in 5 minute interval, that probability is this one, 0.18. Am I right? That probability is very low. Okay, 1 is highest probability, 0.18 is very low. Is that okay? Speak out.
So how to get the tally and then which kind of model we apply this?
No. Whenever they talk about time interval, again this Poisson distribution is mainly applied to time interval. It can be applied to space interval also. Okay, check out Wikipedia. So whenever they talk about time interval, that they are talking about Poisson distribution. And randomness, whenever they talk about randomness.
Okay, sir.
So this is a randomness. Look at here, per hour at a point, he said randomly. Anything can happen. You can talk about probability of 0 bus in 5 minutes, 1 bus in 5 minutes, 2 bus in 5 minutes, or 20 bus in 5 minutes, isn't it?
Sir, it's better to say that it is used for time.
Yeah, if it is given for time interval, you can think that. And randomness, whenever there is a randomness, 20 buses per hour randomly, isn't it? Like that. Now look at here. So the number of particles emitted each minute by a radioactive source is recorded for 10 hours. Okay, can you write down the number of particles emitted each minute by a radioactive source is recorded for 10 hours. Okay, for 10 hour, you got 1800 counts. Is that okay? You got 1800 counts. Is that okay? Question is quite tricky here. Question is, okay, during how many 1 minute interval? During how many 1 minute interval? Look at here. So what he's saying is, first statement, first sentence is, the number of particle emitted each minute by a radioactive source is what you call measured, recorded for a period of 10 hours. Okay, for 10 hours you got 1800 count, but you recorded for each minute actually, then you added that one. Is that okay? You recorded for each minute. Okay, so during how many 1 minute interval?
Sir, repeat the question again.
Look at here. The number of particles emitted each minute by a radioactive source, each minute by a radioactive source is recorded for a period of 10 hours, and total 1800 counts, are registered. Is that okay? That means for 10 hours you got 1800 counts. The question is during, again, so you have divided this 10 hour into 1 minute interval, remember, okay, in the experiment while recording that one, okay. So now during how many 1 minute interval, should we expect to observe no particle? Should we expect to observe no particles? During how many 1 minute interval should we expect to observe no particles? Is that okay? I mean, he is asking the probability. I mean, he's asking, you have to divide this 10 hour into 1 minute interval. How many 1 minute interval will be there? 60 into 10, 600, isn't it? 600 minutes. So in that 600, again, this 10 hour is divided into 600 minutes, 1 minute interval. Okay. So during how many 1 minute interval we expect no particles? Is that okay? That's the question. Now look at here. We shall try to handle this one. First, start this one. Okay. Just looking into question. Don't think that whether you can solve or not. Okay. First, we need lambda to apply what you call Poisson distribution. You need lambda. Am I right? So lambda should be in terms of minute because he is talking about minute here, isn't it? Now, what is that lambda? Lambda is equal to 1800 divided by 10 hour. Am I right? 1800 per 10 hour. Okay. So I have to convert that into 1800. Wait. Into 10 into 60 minute per minute. 3 per minute. Speak out. Lambda is equal to 3 per minute. That lambda is required. Okay. Speak out. Yeah, you were asking something. Okay. Yeah. During how many 1 minute interval should we expect to observe no particle? Is that okay? That's what he is asking. First, we shall find out this probability. Probability of observing 0 particle in 1 minute. Is that okay? That's equal to lambda into tau whole power n e power minus lambda tau divided by n factorial. Lambda into tau is lambda is 3 per minute into tau is 1 minute raised to n equal to 0 e power minus lambda is 3 into 1 divided by 0 factorial, that's equal to e power minus 3. What is 1 by e power 3? This is correct example actually. Look at here. This is too low actually. So I hope you got this one. Okay. Probability of getting 0 particle in 1 minute. Okay. I found that one. 1 by e power 3. What is the nearest value? 0.05. Anyone? Probability of getting 0 particle in 1 minute, that's equal to 0.05, or I can call that probability as 5%. Isn't it? Probability of getting 0 particle in 1 minute, that's equal to 5%. Is that okay? In 1 minute interval. So again, what is the total time span here? This is 600 minutes. Am I right? 5% of this 600 minutes, you will get no particle. Are you getting my point? Now, so what he is asking, how many 1 minute interval, okay, in this one? He is asking this one, okay, because this was the experiment we have done. During how many 1 minute interval should we expect to observe no particle, okay? Now, I got probability that there are no particle in 1 minute, okay? We better write 1 minute interval actually. Then it is meaningful, okay? Probability of observing 0 particle in 1 minute interval, okay? And that probability, that's a 5% or 0.05. I'm going to multiply that with what you call this total number of time, okay? 0.05. What is this one value? Speak out. 30?
30.
Yeah, 30 minute, am I right? That means there are 30 1 minute interval in which we observe no particle. It's quite tricky step actually. Again, it's not usually in exam there are 2 to 3 questions where they ask this one only directly. What is the probability of getting this many event in some time interval? That is straightforward to calculate, okay? But in this question, he asked the question in a quite different way. During how many 1 minute interval in this 10 hour, okay? During how many 1 minute interval should we expect to observe no particle? That means you need to calculate this probability of no particle in 1 minute interval. You have to multiply with total time interval and you will get the time interval. You will get the time about which this 30 minute is not successive 1 minute, okay? There are 30 1 minute interval here, isn't it? It need not be successive. It can be in any order. But there are 30 1 minute interval on which you observe no particles actually. Is that okay? Try to do this one again. Yeah. Again, if you take any radioactive decay problem, this is a radioactive decay problem, isn't it? If probability is not constant, we can't apply this one, okay? This 10 hours should be very, very, very small compared to your half-life. Okay? You are again maybe half-life for this one maybe years of something, so that this 10 hours should be very smaller than half-life. Is that okay? Over this time, your probability of emission should not change. Are you getting my point? In case of this is applied for radioactive decay, am I right? Counts or something, whatever he is talking about, radioactive substance. You have to take care that your half-life should be very large. This time span should be very small. If time span is nearly equal to half-life, what will happen is over some time, your probability will change. Probability of emission will change. That should be very random only. It should not be governed by any nature. Are you getting my point? Over a very large period of time, it is exponential decay, right? E power minus lambda into t, radioactive decay. Okay, that should not happen. That parameter should not come here. Is that okay? That this e power minus lambda into t is not that e power minus lambda into t. Okay, this is different. What I'm saying is there is a radioactive law which governs that radioactive decay. That should not affect this one. Okay, it should be very random only. 1800 counts in 10 hours, very random only. It's not like within first 1 hour highest count and count decreases when you go later. It should not happen like that. This is applied only in case of random events. Is that okay? Are you getting my point? If it is radioactive decay, as time goes, the number of decay will, number of count will decrease, am I right? That should not happen. Is that okay? Suppose if its half-life is 20 hour, okay? 22 or 30 hour. Then what will happen is, if you start at a clock, okay? Within 10 hour, okay? Within first hour, whatever count you get, so in the next hour, your count will decrease actually. Suppose let me take half-life is years or suppose around 100 years. Is that okay? For this substance. Then within 10 hour, usually your count will not, decrease or something. Okay? So that's why you take counts are random here. 1800 count very randomly in this 10 hour. Is that okay? Speak out. That randomness is preserved, as well as again probability is also small. You can see this one. This is the best question. Look at here. Let me take one more question. Suppose you receive an average of 4 phone calls per day. Write down. Suppose you receive an average of 4 phone calls per day. Four phone calls per day. Lambda is given. Okay. What is the probability that on a given day you receive no phone call? What is the probability that on a given day you receive 0 phone call? Speak out. Lambda is equal to 4 per day. Isn't it? Lambda equal to 4 per day. 0 phone call in 1 day means lambda into, so tau equal to 1 here. This is tau. Lambda into tau whole power n e power minus lambda tau divided by n factorial. That's equal to, lambda is 4 into 1 day raised to 0 e power minus 4 into 1 divided by 0 factorial, 1 by e power 4. So next question is, what is the probability of getting 1 phone call in 1 day interval? Now it is 4 into 1 raised to 1 into e power minus 4 divided by 1 factorial, that's equal to 4 by e power 4. Can you answer this kind of question? Application, okay? I'm just working on application. Now let me start with what you call binomial distribution, okay? That means, can I write this one like this? Probability that n events in a unit time interval, okay? Okay, if time interval is unit, lambda into tau power n e power minus lambda into lambda divided by n factorial. So tau equal to 1 here. Unit time interval means tau equal to 1. Okay, let me take like this. Then your Poisson distribution will be like this. Tau equal to 1. Tau is there, but it's equal to 1. Okay. So now look at here. If you take your binomial distribution, probability after trial, n success. Okay. So that's equal to n c n. Can I write like this? P raised to n, q raised to n minus n. Is that okay? Q raised to n minus n. So now, if n is very large, okay, or this small n is, this is very much smaller than capital N, okay? This one. This n is very large, okay? Very, very large. P is very small. Okay? P is very small. P is less than 1, Shall I write like this? Small means less than 1.
Success is
Probability of success is very small. Okay, we are talking about only about success. You can write 1 minus p here. Okay, you can write 1 minus p here. 1 minus p whole raised to n minus n. Is that okay? N is very large. Small n is very much less than n. Wait a second. I think I need some more. Unless we derive, I'll not remember anything actually. With np remains constant, okay? With np, n into p nearly equal to constant. Is that okay? P is very small, but n into p is nearly equal to constant. Not capital, that should be capital N. Wait a second. Again, the symbol difference. Capital N into p. Is that okay? In that situation, okay, n tends to infinity. Okay, in the limit of n tends to infinity, okay, p is very much less than 1, but n into p we maintaining that one as constant. Okay, in that one, so this will tends to. Okay, so can I write like this? n p raised to n 1 minus p raised to n minus n. Okay, that's nearly equal to, okay, n into p whole raised to n multiplied with e power minus n into p whole divided by n factorial. What is this one? This is average. This is average n into p, average n. Let me call that as average as lambda. Lambda whole power n e power minus lambda divided by n factorial per time interval. We are talking about per time interval here. Is that okay? So why I defined that one? Because here I can't talk about time interval, but actual Poisson distribution can be derived for time interval. Okay, so here we need to discuss about per time interval actually. So you just have to remember this one. In this limit, okay, binomial distribution tends to Poisson distribution. You just have to remember this one. Okay, I mean you don't have to do that one right now. Okay. So this is not large. Okay, this is equal to constant means this is not large. N into p is not large, not too large. There's some finite value. Okay. Look at here. The same thing. Have you written this one? So shall I rub it out? The same thing. N is very large. Okay. N is very large. And NP is also very large. Is that okay? And NP is also very large. Here we again in the Poisson distribution we have taken NP nearly constant. Am I right? Here N is very large. NP is also large. Okay. In that case, what will happen here is, look at here. Your binomial distribution, N C N. Okay. P raised to n. Sorry. N C N. P raised to n. 1 minus p raised to n minus n. That is nearly equal to. Okay. That's nearly equal to 2 pi npq raised to minus 1 by 2 e power exponential of, look at here, minus n minus n into p by 2 times npq. This is squared by 2 times npq. We call this as Gaussian distribution. We call this as Gaussian distribution. We better to make some substitution. What substitution we can make? Because again, this is now, look at here, this is a kind of continuous distribution now. Okay, you have to make it continuous distribution. How can I make it? n minus n into p, isn't it? It's a continuous function of n actually. This was discrete, am I right? Again, you have to define for one, you have to define this one for integer value, isn't it? N equal to 0, 1, 2, 3 and so on up to n. But you can define this one for any n actually. So that's why I better to make it as a, what you call, distribution. Some more factor will come, okay? Look at here. We are going to write p of x into dx. That's equal to 1 by root 2 phi. This one, 1 by root 2 phi into 1 by sigma. Because 1 by n pq, that is standard deviation, n pq. So that was standard deviation in case of binomial distribution, okay? 1 by sigma into e power minus of x minus mu whole square divided by 2 sigma square. This is sigma square, look at here, 2 into n pq. He has written this whole thing as n minus mu. Let me define that one, okay? Divided by 2 sigma square dx. This expression is converted into this one. This is Gaussian distribution. Centered at x equal to mu. Wait a second. Mu should be defined as, mu is average, am I right? Mu should be average, isn't it? Mu should be average. Mu is equal to n into p. Yeah, he defined correctly. Divided by 2 into standard deviation. But whatever the problem regarding this one, okay? So they will mention what you call, this is Gaussian distribution. Again, you know whatever the average value, whatever the quantity you can calculate, am I right, using integral, okay? He defined sigma correctly. Sigma is, no, he is converting everything into displacement actually. Is that okay? So this n is not displacement, it is number of steps to the right or something here, isn't it? But he want to convert that everything into x equal to m into L. Actually, m is equal to 2n minus n, am I right? 2n1 minus n, whatever, okay? So that's why the whole structure he edited and he has written sigma as, okay? So from here, he has taken this one and he edited this one. Sigma is equal to 2 root npq into L, or you can write it like this, sigma of x actually. Root of 4 n p q L square, you remember? And this mean value is actually x mean value. That's equal to n p minus q into L. I hope now it makes sense, isn't it? It was in terms of n, but he converted into x actually, because again, we don't count number now, okay? Now once it is continuous distribution, our steps are not what you call discrete now in terms of L, okay? It is almost continuous now. Is that okay? We have taken very large number of steps, okay? And our average is also very large, okay? Average number of steps to the right, everything is very large. Then that again, you can take that each of length, this L is very small now. Is that okay? So compared to the whatever the distance we talked about, so then we convert that into continuous distribution, and that's a Gaussian distribution. You can see it's a Gaussian function. Sigma here, okay? Sigma of x actually. Sigma of x actually. He didn't mention, but later he mentioned it. So mu means x mean actually. Is that okay? So this is a connection between binomial distribution. In this limit, it will become Gaussian distribution. So these are the connection. These are the parameters we use in case of binomial distribution, isn't it? But once we go for this distribution, once we try to apply this distribution, we don't talk about binomial distribution, okay? We apply this one as it is, okay? Just like when we are applying Poisson distribution, we don't talk about binomial distribution. This is just in one limit, it will go to what you call Gaussian distribution, okay? In this limit, it will go to Gaussian distribution. I think this is just what you call remembering part. You don't have to apply this one, okay? And any application that comes, take the distribution, normalize. You know how to normalize, isn't it? If there is no factor like this, okay? Normalize and find the average values, okay? You know that one. So for this again, I'm referring Reef first chapter only. He has done all of this mathematical derivation. So I'm not doing that one, okay? We just, it's okay, it's sufficient, okay? In this limit, it will become like this. In this limit, it will become like this, okay?
Sir,
Yeah.
sir, you said that when probability is small and constant, we have to apply Poisson's distribution.
Yes.
Sir, but what applies when probability is large and not constant?
No, then you have to deal with binomial only. If this is very appreciable, then you have to deal with binomial distribution only. Is that okay? Then you can't approximate it to what you call Poisson distribution actually. Is that okay?
Okay, sir.
Sir, in case of Gaussian, we can calculate averages and
Yeah, if you calculate average, you will get mu only.
deviations.
So if you calculate deviation, I think you will get this one only. This itself is deviation, I think. Check that out. This whole thing is normalized distribution.
In case of Poisson distribution, how can we calculate those deviations or?
I think then we have to define it like this, isn't it? We have to define P of n is equal to lambda power n e power minus lambda divided by n factorial. Then you have to take n average, n square average, isn't it? So this is actually discrete probability distribution. This is also discrete probability distribution. Is that okay? Speak out. This is also discrete, am I right? You are talking about some particular event depends on n, but this is continuous. Here you need to do integration. Here you need to do summation as before actually. But I don't think we can derive any generalized formula. Let me check that out, okay?
It is too large.
N is too large, okay? But NP is, capital N into P is not too large. This is equal to some constant value, okay? That's the small difference between from binomial to Poisson, binomial to Gaussian. Is that okay? Once it comes to Gaussian, you have to do integration. It's a continuous variable. So Poisson distribution is discrete variable only. Isn't it? P of n. That's how we define. Is that okay?
Sir, can
Yeah.
you plot this probability with lambda?
No. For a given lambda, you better to plot with different n actually. For given P and Q, you plot for, for given n, you plot for different n here, isn't it? That's a distribution. For given lambda, you just plot this one, change lambda, then plot again, then you can compare. For different lambda, what would happen? Are you getting my point?
Yes, sir.
If you change lambda, obviously you will get some exponentially decaying kind of thing. But for one lambda, plot this one. For other lambda, plot this one. I think what will happen here is, again, I can't guess that one. Lambda power n by n factorial, am I right? I can't guess. Anyway, let me try that one, okay? But there are not much questions. That's why I'm in hurry, okay? But Poisson distribution applications are there, and there are questions on this Gaussian also. But you do it like ordinary. You are just like you do in case of ground state of harmonic oscillator. Is that okay? That's also Gaussian, isn't it? You do it like that. But remember, this is probability density. Don't take mod square, okay? This whole thing is a distribution function. Equivalent in quantum mechanics, it's mod psi square, okay? Don't make it mod square again while normalizing and all, okay? This itself is probability per length, okay? P of x dx. Is that okay? Don't make it mod square. There we need to make mod square because that interpretation is different, okay? Be careful.